and to D the displacement vector that describes fields in describes electrostatics in dielectric. Dielectrics, we already studied a lot about conductors, so now we're going to discuss about the dielectrics mainly, and especially emphasize the polarization. And to start this, I need to continue what we started the previous lesson and discuss what is a dipole. So let us discuss the multiple expansion. So physically, what is the idea? The idea is very simple. If you are very far away from some object that has some charge on it, you can approximate the charge on this object due to separation of scales, the scale of the object on which there is the charge and the far distance where you are looking at. So if you look at many things from far away, you see something which is an approximation, but this is an excellent approximation. If I look at you far away, I don't see your hands, I see you as some kind of rod, more or less, and that's a good approximation. That is the idea. So the idea essentially starts, let's say we have a simple system, we have 3 charges, plus and 2 minuses, let's say all of them have the same charge. And then I ask, I have a scale here. The scale here is the scale of the system. This is, I call it A. What will happen far away from the system? So I look at the distance R. What will happen? Of course, if I look microscopically inside here, there will be a very complicated set of fields due to these 3 charges. But far away, it will be very simple. And what will be the charge here? It will be -1, and what the potential will be, it will be exactly like the Coulomb potential. So it will be effectively like a system with 1 minus charge, that is. And this is called a monopole, so we like to give names to these things. This is eventually will behave like a monopole. Mono means unique, one mono. Monopole means 1 charge. And the potential, we all understand, will go like 1 over R, the famous Coulomb potential. Now you can ask the same thing, what will happen if you have different configurations of charges? So for example, what will happen, this is the famous dipole. Then I look again at some large distance, and then what will happen, what will be the potential, how will it go? So it's more complicated, the Coulomb potential, because it will depend also on the angles, because I have here a vector, it will depend on all the angles. But let us just concentrate on the distance dependence. I think you know this, and soon we'll show this. This will behave like V of R, maybe more correctly. This is not alpha, this is going like 1 over R to the power 2. This is a dipole. How does this come from? It will come from some Taylor expansion that we will soon show of the original Coulomb potential. So this individual guy gives you potential, which is the Coulomb potential. This one also Coulomb potential, but we will expand. And here again, there is this distance. Now it's this distance here, A. And then this is valid only at large distances when R is much bigger than A. So this is far away distance. This is a dipole. What after a monopole and a dipole, what happens? Quadrupole. So notice that there is no tripole. There's no such thing as a tripole. There is a quadrupole. The quadrupole is composed of 2 dipoles. The quadrupole, I can plot it like this. Plus, minus, minus, plus. So this is a quadrupole. Maybe there's a spelling. And at large distances, V of R is going like R to the power 3. And this is due to the potential of 2 dipoles that are slightly separated, etc. What happens after the quadrupole? Octopole. So you jump here 1, 2, 4, 8. The octopole is something like this. This is a cube in my humble attempt. So here I have plus, minus, minus, plus, and here minus, plus, minus, plus. So it's two quadrupoles, one on top of the other. This will give you this. And this is the basic physics. Okay, so now what do we want to do in principle? First of all, this is a very descriptive description of the system. In general, we don't have these three charges. A dipole is not, in the real dipoles, are not one charge here and one charge there most of the time. This is just idealization. A dipole can be, for example, a dipole can be, oops, I'm reading on the line, a sea of electrons surrounded by, let's say, a point charge, which is the proton, which is distorted, the sea of electron, one electron. This is the, like the wave function, if you want, the modulus squared. This is the density of the electrons, let's say, in the hydrogen atom. We'll soon discuss it a little bit. But assuming that the charge density is something like an ellipse, this is also a dipole, and it can be much more complicated if you have, let's say, a water molecule. That's also a dipole. And you just, if you just think about what are the charges in a water molecule, so the water molecule looks something like a V for a physicist, and around it a lot of electrons. It's super complicated. So the basic question is, given a charge density rho of R in some material, what are these contributions? The monopole, the dipole, the quadrupole, the monopole. The monopole is going to be trivial. We are not going to discuss it so much. That is the question. What is V of R at large distances? And again, what is large? Every time someone says large, you need to compare it to something. Large compared to the size of the object, which is this object, which is a general object on which there is some charge density. That is the basic question. And how do we treat this? We treat this with a multiple expansion. So this potential that I'm going to find has many contributions. In principle, it has a monopole contribution, and then it has a dipole contribution, a quadrupole, octupole. But don't worry, we will usually stop. We'll say the total charge is 0, then there is no monopole, and then usually we stop on the dipole. And then if you want to be tortured, we go to higher order terms, but usually this will not be done in this class. Although it can be important in principle, but I'm just showing you the principles. So the game is, again, the system is not charged. What I mean is the total charge, of course there is some charge, but the total charge is 0, then the monopole will vanish. That is the case that mostly we are interested in, and then you have the dipole. So how does the field of this is the idealized dipole that we can easily understand, because this is just a superposition of two charges at two different places at distance d, and then each one of them satisfies the Coulomb, so we just add fields. In principle, this is the general field lines. So we have these field lines. So the particle is attracted to the minus, and it is a positive particle will be repelled here, and then these guys will be something like that. Oops, I'm not going to plot it. You should look at it this. And what do you see here? For example, in the vicinity of the two charges, sorry, here it's like that. In the vicinity of the two charges, you just see the Coulomb potential, because the other charge is negligible. So you see the density of the lines. Well, there's only two lines, but you see the density is very high there. What does it mean? It means that the electric field here is, of course, very high, because it's simply the Coulomb field. And same here with the different direction of the arrows. And then you have these loops, and this is related to this fact that on this line, eventually, as we are going to soon show, the potential here will be 0 along this line. Soon I'll show that. Okay, so this is a simple intuitive picture of dipoles, quadrupoles, etc. Now we want to do the math in order to find this multiple expansion. And the math is pretty simple. And it's based on essentially the cosine theorem. And we have a tool. We need a tool. I have it a mouse, but I don't think it's good to clean the board with a mouse. Where is the... Usually there was one here. I was lazy today, I didn't bring mine. So the multiple expansion is based on two things. One of them is the cosine theorem, and the other tool is, what is the other tool? Yeah, the Legendre polynomials, where there are several multiple expansions. We are using actually the simplest one. There is a second type of multiple expansion, multiple expansion, which is based on YLMs. But I'm going to show here just on polynomial Legendre for simplicity. The other one is as important as this one, and sometimes also very useful. So, okay, let us start with something simple and then generalize it. And the simple thing is simply idealized dipole. So maybe you saw this, I guess you did. This is Q. This is minus Q. And then this is not a general charge density. These are 2-point charges, the simplest case that you can imagine. And I plotted here the Cartesian coordinate system, and this is the z direction. I'm not going to write all the symbols because otherwise it's going to be very ugly. And then you look at large distances at some point here. So here is my observer, and this size, this separation between the two charges is called d, and d is the small scale, and the location of the observer is the distance from the origin, where here it's very easy to identify where to put the origin. There is a small issue, where is the origin? Okay, so we stick it, because we are physicists, we stick it here exactly in the middle. I'll discuss this choice a little bit later, but there is a delicate point here. How do you choose the reference frame? It's not too delicate, but we can choose it like this if we want. So this is just a matter of definition, and here I'm going to define this R plus. R plus is between the plus charge and the observation point. And then, of course, we have, R minus, and then we have another vector because we like 3. And that is the location of the observer relative to this reference frame R. So we have R plus, we have R, and we have R minus. And we also have an angle, and we will define this angle as theta. Then what is the cosine theorem is like, okay, R plus minus. I'm going to do it simultaneously. For R minus, you don't use theta, you use pi minus theta. But that's easy to do. So R plus minus, I think you understand what this is. This is either R plus or R minus. I'm going to do it simultaneously. This is equal from the cosine theorem to R squared plus D over 2 squared. So let's say R plus, and here I have R, and here this is D over 2. These are the angles, and then I need to subtract. Now it's 2, but here is D over 2. So it's easy to see that this is dr cosine theta. And that is the cosine theorem. Theorem or law, I don't know. Maybe theorem is too much for this cosine, but I guess when they invented it, it was very nice. So let's call it cosine theorem. So, and then what is VR exactly? This is the famous 4 pi epsilon 0, 1 minus R plus, minus 1 R minus, and here I have a charge Q. So the key issue here is that these two guys have different distances to the observer, so this is why I use here 1 over r plus and 1 over r minus, and this is just the Coulomb field, nothing else. This is what you learned in undergraduate, in kindergarten, I mean. So this is of course obvious, and now what you do is very simple. We have here r plus and r minus, so we need to insert it here, and what do? We expand, we Taylor expand. So before I said that cosine theorem is important, but also Taylor expansion is important, and this will give you a distance. Now, to zeroth order approximation, what is zeroth order approximation? When r is gigantic, or the leading term, what is r plus and r minus? What is the biggest term in these three terms? R squared. So if I just take r plus and minus as r,
0.
it will give you 0, and that will be, that's the monopole that is vanishing here because the total charge of the system is 0 here. So this is to be expected, of course. So the leading term will give you 0. And then what you need to do is to calculate the next term, which will be the dipole. So let us look at this a little bit. You have this 1 over r plus or minus. I just insert the cosine theorem, and let us write it like this. I'm taking the r outside, and here I'll have a square root of half. So I took r squared out, and I took I need to take the square, the root of this thing to get r plus or r minus. So I do it, hopefully this is clear. This is d over 2r squared minus plus d over r cosine theta. So I use this one, and I hope you can see this. Why did I do it like this? There's a small benefit here. Here I have the famous 1 over r of the Coulomb potential, and inside here I have quantities that are dimensionless. D over r has no units, d over r has no units, and now I can say what is big and what is small, because I can compare d in units of meter with r in units of meter, and then obviously this guy is small and this guy is small. But when you look at this, you see something which is the following. There are two terms. Which one is the bigger term, this one or this one? It's of course, this is the smaller one, this is the bigger one, because this is d squared over r squared. You can argue that for a special cosine, this is not the case, but what we are going to do is we're going to say this is the leading term. So this from here will come the cosine, which will come into the expression of the dipole approximation. So now we need to expand it. So what is this expansion? What do I have here? It's a very simple expansion, and later we will expand it a bit more and more generally. So what is this Taylor series expansion? What is x? X is some small number. This is 1 minus x, and later we will have higher order term. The higher order terms will give you the quadrupole, etc. So this is a very simple Taylor expansion that I think you all know. So okay, let's do this. Then this 1 over r plus minus is equal 1 over r, and I have here multiple 1 minus, so this is minus, this will turn into a plus, plus minus d over r cosine theta, and then there are more terms, which for now I'm lazy. I'm always lazy, but now I'm very lazy, so I'm just going to have the first term. There are d squared r divided by r squared terms that I neglect now. Now, what do I need to do here? I need to subtract. So when I subtract the plus and the minus, the leading term is the same. This is this 1 over r. Then they will be subtracted. They will vanish, as I already said. And what will remain is this term, the first term that is not trivially 0. And then if I do that, I just plug it into here. Then I have something that I'm going to call V dipole r, where V of r is approximately V dipole. And V dipole by definition now is given by QD why didn't you tell me that I made a mistake? Here's the 2. The 2 is important. This 2 comes from this 2. And because I have 2 terms, 1 over 2 multiplied by 2 is 1. And then this is this d over r with this r squared cosine theta. And 4 pi epsilon 0, of course. So this is the potential of a dipole, a specific dipole of 2 points with d distance between them, and each one of them with a charge q, one with plus, one with minus. And this dipole has now this new thing. I mean, we said already it will be like 1 over r squared, but now we have the full expression. It will be, the potential looks something like, if this is plus, this is minus, this is theta equals 0 up here, this is theta equal pi down here. So here the potential is negative, assuming q is positive. V is less than 0, here V is, and here it will be 0, and cosine is here pi, here theta is pi over 2. So on this there is a cosine going on here, so the cosine is oscillating around this circle for a given r, and then the further away you are, the potential goes down, meaning the force, the electric field is smaller and smaller, as you might expect. Okay, so now we have this expression, and it's very simple, and I think maybe you saw it previously, but now the big question is, how do we generalize it for a general charge distribution of some material? More formal expansion of this thing. So now we're going to do that, which will give you some final expression, which is not as simple as this one, but, and it looks a bit different, but it's more or less the same from a philosophical point of view. What I mean is that eventually you will be left with some integral represented the dipole moment. The dipole moment in general is hard to calculate, but we will be able to write what it is as an integral, and then we have this equation more or less that we had here in the simple case. Okay, so let's do this exercise. And for that we start with the definition of the system. So now we want to do the multiple expansion. It will be slightly more general than what we did, because we will also not stop in principle after the first term. We have the full expansion. So the reference frame that I want to do, I'm defining first of all some reference frame, and I have here some charge density rho of r prime. So I have here a unit volume d tau. So let us write this. What do I mean by this? I have, this is the origin. It's not far away really, and this is r prime. So r prime is some point usually representing the charge, the location of the charge. In principle, it can be over all space, but what we need to integrate is only over this volume where the charge is located. So this is r prime. It's a vector. And what is dt prime? So around this thing here, there is, as usual, some delta tau. Delta tau, remember, these are the notations of Griffiths. This is an element volume. So I just build a small box here. And inside there is some charge. What is this charge? It's given by this density, rho of r, whatever it is, rho of r at some point multiplied by delta t, delta tau. It's a three-dimensional volume, gives you the charge in this place. And then you need to add contributions all over the thing. Of course, here we are assuming that we know what is rho of r. Someone told us, someone took some charge, stuck it on the wall, and we know this charge. So what is, now we need to add some other, this is r prime, and what we are interested in, this is the observer, and this is point r. Maybe what I'm doing here is correct, but maybe better if the reference frame would be inside or close to where the charge here. What I'm going to assume is that this scale here, there's a scale here, is much, much smaller than this distance. So the position of the we are interested in is r, and this is going to be L. L is also a vector, which is going to change when we add contributions from different elements inside here. So this element gives you one contribution, then let's say this element, there's a different L. We need to add all of them up. But we know how to add things. Adding things is doing integrals. That's addition. So we can write formally the solution V at point R. This is simply the Coulomb law, is 1 over 4 pi epsilon 0. Integral over the volume. What is the volume? The volume is this object where the charge density exists. 1 over L rho of R prime d tau. And again, this is a 3 integral in a 3-dimensional space. And all the symbols are the usual symbols. So, okay, this is the solution. I can go back home. Maybe, let's say, if the density is complicated, I can, in principle, solve this numerically, for example. It's not out of the question to solve such things numerically. Now, the point is, again, like before, is to use the cosine theorem. So this L here is given by these two vectors, r and r prime. R prime is the integration coordinate, r is the location coordinate, and for the cosine I need another angle here, which is this theta prime, which depends. If I move this location, this theta prime is changing, right? And if I go here inside, this theta prime is changing. So this theta prime is a rather complicated thing. It depends on what r prime you are in. But for now, we're just going to write it like this. And the whole trick here, in my opinion, one of the nice tricks is we're going to get rid of this theta prime eventually, which is the complicated part. But from the cosine theorem, what do I know? I know that this is r squared plus r prime squared minus 2r prime cosine theta prime. Okay, so now we need to do some math, which is very similar to what we had before, but now we are going to do it more professionally. So remember, before we had the dipole, potential is proportional to cosine theta. When you see a cosine theta, what do you think about? What? The first polynomial Legendre. Of course, most of you don't think like that. So maybe if you see a cosine, you think about the sine, something else, or I don't know what. But this is the motivation. We have to expand further, and maybe by luck we will get the polynomial Legendre. This is exactly what is going to happen. And so now we are doing exactly like we did before, but we are going to be more stubborn and we're going to expand more. That's all. So this is 1 over r, like before, and then like before I have some square root. Inside here I'll have something that which has no units, because the units of L and R are the same. And this is, of course, seen already from here. And then I have here 1. This is, I took this 1 outside of this square root. And here I have, I'm going to write it like this, R prime R. So this is this term multiplied by R prime r minus 2 cosine theta. So you see, for example, put this r inside. If I put it inside, I need an r squared because of the half. R squared divided by r times 2 will give you this term. I think you can see this. And I wrote it like this. And now I'm going to call all this guy, I'm going to call epsilon. Why epsilon? Because epsilon is a small number, and r prime divided by r I'm going to assume which is small, which means that effectively I'm going to build the coordinate system close to this system, in the middle of the system, somewhere. It doesn't matter where, and later we will discuss why the reference frame is not important. But I assume now that this r over r is much, much less than 1. So epsilon is much, much less than 1. Epsilon has no unit. So let us expand this. So what do I need to do? I need to look at the expansion of 1 plus epsilon to the power half. And then this one is, I already mentioned, the first term is epsilon over 2. What is the next one? Epsilon over epsilon squared. This is the Taylor expansion. And what will we have here? This, of course, maybe you don't know, but if I remember correctly, it's 3 over 8. The 3 comes from the fact that when you take a derivative of half, you get 3 over 2, and then you need another derivative that will give you the 3. And the 8 is from the 2, and there's also in the Taylor expansion 1 over 2. But let me check that I didn't make a mistake. No, this is correct. And there are more terms, and you are invited to calculate these terms if you are very much interested. It's very easy to continue with this. You just put it in ChatGPT, please expand 1 over epsilon half, and it will give you the full expansion. It's very easy to get, and you can also do it with no special problem to calculate these numbers, like 3 over 8, 1 over 2. Okay, so here at least I don't see the Legendre polynomials, but let us now insert this in there. So I have 1 over L is equal to 1 over R, and then I take this thing as 1 minus a half r prime over r prime over r minus 2 cosine theta. This is what I called epsilon, all this thing, and then I have here plus 3 over 8. This is this 3 over 8, and now I need to look at cosine squared, at epsilon squared. R prime over r squared, r prime over r minus 2 cosine theta squared, blah, blah, blah. 3 dots for all the rest. Now here we have to be a little bit careful because there are mixed terms. Because if I consider the small parameter as r prime over r, for example, this term multiplied by this term is a second term. It's r prime over r to the power 2 compared to r prime over r times cosine theta. So we want to organize this a bit so that we have an expansion which is consistent with the small parameter. So this is 1 over r. So what is the leading term? It's 1 minus, okay, there's no half. 1 minus r prime over r cosine theta prime. So this comes from here, multiplied by this, and 2 and 2, and there's a plus here. Yeah, let's write epsilon squared. And then there is another, the next term is r prime over r to the power 2. And here I have 2 terms, right? One of them is this one. How do I want to write it? I'm going to write it like this, half. So this one comes with a minus sign. So here I have r prime over r squared with a minus sign. So here this will be minus 1. Now I need to look at this guy. What is the contribution here? Where does it come from?
4 cosine squared.
It comes from this guy when I square things. So this term in principle gives you this to the power 2, but this will be r prime over r multiplied by this is r prime over r to the power 4. I throw it away. There's a mixed term, but that will give you r prime over r to the power 3. I also throw that away, and I'm just left with this guy. So this is 2 to the power 2 cosine squared, and this is multiplied by 3 over 8. 4 divided by 8, 4 over 8 gives you half. So here I'll get 3 cosine theta squared. Sorry?
That's the Legendre polynomial.
Yeah, that's the Legendre polynomial.
Yeah.
Exactly, that's the Legendre polynomial. So we are so happy. So this is the point. Now, I didn't prove that if you continue this way, but the answer is if you continue this way, you'll get also the... Of course, if you look at the literature of the Legendre polynomial, maybe you'll find that this is not surprising. Maybe this is the generating function of the of these polynomials. But the nice thing is here that we got it from basic Coulomb potential. Okay, Coulomb was a French gentleman, and Legendre was also a French gentleman, so they lived more or less, I think, the same times. It's not totally a coincidence, even though I'm not sure what came before, who came before who, but it doesn't matter. Okay, so Pn of x. What is Pn of x? These are the Legendre polynomials, and this is the n, the index of the... This letter P is very annoying because later P will be for dipole, but here it's for the polynomial. So if n is equal 0, this is just a table, this is 1. And if n is equal 1, this is x. And remember, this x is actually the cosine theta. And if this is 2, this is this expression. It's 3x squared minus half, and I never remember, is it with the 2 or without the 2? Yes, it's with the 2. And of course you can build it. So this is just a table. So we are very happy. We identify these terms. This is the first Legendre polynomial. This is the second. Continuing this way, we get a very useful and well-known equation, which I just actually wanted this. So maybe we'll leave this. Let's write it here. And this is the 1 over L. Again, L is this distance between one point inside the material. And L now is not a vector, it's the absolute value of the vector. 1 over L is equal 1 over R, which is expected when the distance is very big. It's nearly, put this on the moon, then this L and this R are more or less the same. Sum n equals 0 till infinity, Pn, which is the polynomial Legendre cosine theta, r prime over r to power n. So again, here inside there is something which has no units. In our this is general. I mean, in principle, r prime over r does not have to be too big, but what we do in practice is we assume that r prime over r is a small number, and then we can expand it to the first term, the second term, the third term, depending how much energy we have or how much we want to torture the student under my supervision. We can do it to higher order terms, but usually we stop at some point, or we let a computer do the calculations in higher order terms. So this is a useful expansion. And now what I have to do, I take this one and insert it in this one. Then I need to integrate again. Integrate over all the elements inside our body. Okay, this is it is what it is. You know, it's maybe it's nasty, but let's do it anyway. There's no hope to solve this exactly because I'm even not specifying what is rho of r prime, but I can be a formalist and still get some general insights. So what is v of r? In principle, I can write it as an infinite sum. So it's a bit crazy because I have one integral and now I'm going to have infinite number of integrals. But the nice thing is I can throw away many of the integrals. That's the basic idea. So this is 4 pi epsilon 0. This is just here. 1 over... Now I do a small trick. Okay, here there's Rn and r to the power n and r. So for physicists, we're going to take it outside of the integral because the integration, remember, is only about the r prime. So it's convenient to take it outside. Of course, here I need to sum n equal
0.
Yeah, 0 till infinity. Yeah, soon I have to comment on this. And then I'm left with the following integral over the volume d tau. It's a three-dimensional integral like a usual thing. Rho of r. This is this rho of r here. R prime. What do I have here? Pn cosine theta squared. That's it. Sorry, r prime to the power n, this one. So this is the now an expansion of this potential, and you see here all the orders of 1 over r, 1 over r, 1 over r to the power 2, 1 over r to the power 3. You pray to God, I hope this series converges. Or we ask our mathematician friends, go prove that it converges. After 25 years they come back, but no one cares anymore. More or less. No, it's not true. It's interesting to check these type of things, and maybe it's easy or difficult depending on the mathematician. But in physics, what we do, we cut it off. We look at the lower order terms, but again, under the condition that we look at large distances. We have to obey the assumptions made in the derivation. So the first term, the n equals 0, is the monopole. What do you mean is the monopole? It's not the physical monopole, it is the term from which we calculate the monopole contribution to VR. And the n equal 1, this is just a dictionary, this is the dipole. And the n equal 2 is the quadrupole, etc. So people will ask you, here is some density, find the potential, then you come back, I can't do this. Okay, so you can find the monopole contribution, the dipole contribution, the quadrupole, etc., etc. The integrals become more and more complicated. Here you have this n here, and here we have this polynomial Legendre. Do these integrals, and God bless you. So when n is equal 0, this polynomial Legendre is simply 1, and this n is 0. So if I have d tau rho of r over the volume, then if this is 0, if equals 0, no monopole, which is of course what we expect. If the charge integrated overall volume is 0, there is no monopole. It doesn't mean that there's no charge. For example, here half, up here everything is plus, down here everything is minus. The total charge is 0, then the monopole is going away. This is the situation that we are most interested in, because the monopole is also a trivial example, because if I have here n equals 0, then it's 1 over r times some full charge, and that is simply the Coulomb's law. So everyone can see that n equals 0 is exactly the Coulomb's law but only far away. And the charge is this integral. So let's assume, mostly we'll assume that this is 0. And then the leading term usually, of course also the dipole can vanish, but in many cases it does not. Then the leading term will be the dipole. And this is what we are going to focus on. And this is this dipole, V dipole. It depends on R. This is, if you want the definition, it's just the second term in this expansion. It's 1 over 4 pi epsilon 0, 1 over R to the power 2, which was exactly what we had also before. So this Coulomb potential 1 over R, this is 1 over R to the power 2. And then you have integration over the volume, where all the charges are. Now I just need to use polynomial Legendre, which is this cosine, and it's cosine theta. R prime, this is this one to the power 1. Rho of R prime, which I don't know, d tau. This is the dipole. In principle, this is the dipole approximation for the potential. But now we are going to write it in a slightly nicer way, because this is pretty ugly with this theta here, and it's nice, but it's also very simple. And this is the following fact. I'm going to use slight change of notation. This is of course perfectly fine, but we want to do it and write it somewhat differently. I'm going to notice the following great, no, I'm kidding, R prime. So this is R prime. You see I have here this vector, and this is R. And actually I want to do it the opposite. R prime, R. What is R? These hats are very important. These are unit vectors. Their size is 1 in this direction. So I think you know about this small hat notation. This is the meaning of this thing. What is this thing? Exactly. So this is cosine theta prime. Then I can use this one. I just write it as R prime dot R, and then I have here, you see, R prime hat multiplied by R prime. What is that? That's R prime. So I'm going to also use R prime is R prime, the size of this vector multiplied by the hat. This is just definition. And then I'm going to define this P. What is P? It's not momentum. It's not polynomial Legendre, which is a vector. It is the dipole. It's not polarization. It is the dipole of this system. The dipole associated with this charge distribution here. So this is P, and this is actually going to be small p. There's also going to be some big P. So this is the dipole moment. This is the dipole itself. What was the dipole before? We had two charges, Q minus Q. It was D times Q. So the units of this thing is the same units. It's charge multiplied by meter. Same thing, but now we have a complicated charge distribution. So we are going to define this as the following. We have here integral over the volume over this thing, and d tau. So I need to add up all the contributions of R vector rho R prime. I'm not saying that in general doing this integral is easy in any way, but formally this is the solution. And what does it mean? So you see here I have delta t times rho of R. Rho of R is charge per unit volume. Delta tau is an element volume. That is a small charge. This position R prime, and then I need to add all of them up to get this dipole moment P. And then you see this one, when I do this change R prime, I can easily write the following. You will hopefully see, and if not, I'll kind of try and explain, but I think it's pretty obvious. I mean, this is P dot R divided by R squared. So what is this? What is this P? How do I think about it? You can think about it that here microscopically there are many small dipoles like the one that you are used to with 2-point charges. And you need to add all of them in a small box, and then this is each one of them, and then this is the total dipole, which comes up from vector summation of many dipoles. So this is of course, this is the definition of this. A cosinus po. So again, let me repeat. I take this R prime, I write it as R prime, and then to get this cosinus, I delete the cosine and I multiply by this vector R hat that is here. So this is exactly the point. I want to get rid of this cosine, and I get rid of it by going into this vector notation. It's not that it is not there anymore. It's there. It is here. But what is the nice thing about this? You see, P is a property of the medium. It's independent of theta prime. It is independent of R. It just, you calculate it and then you can move different places. It doesn't matter. This is a property of the problem itself. Then R is where you look at, and then if you know this P, you multiply by R, you get the result. Of course, theta is hiding here. Where is it hiding? In this small dot. It's there all the time, but by this formula, you first calculate this dipole moment, and then for different R's, you have the potential, and that's it. So just for sanity, we can check that this result is the same that we had for the simple problem. This is a, you should always check if you get the same as the simplest problem, if you can imagine a simple problem. And what is the simplest problem is that these 2-point charges that we had at the beginning of the class. So then in this case, simple problem is like this. And we have here plus, and here we have minus q, right? And what do we need to do? We need to write the density of this system. And writing the density of this system is not too hard. What is the density here? What is sum of 2 delta functions, and these are 3-dimensional objects. So what is rho of R, if you want, R prime, in some coordinates that you understand. This is delta. It's a delta function of Dirac, z prime plus d over 2. The plus here means that z is minus d over 2, and this is where I put the minus charge. So I choose the minus charge here. So this is d over 2, and of course up is d over 2, plus delta z prime minus d over 2, delta x, delta y multiplied by q. So the charge density is, of course, each one of these delta functions has units of 1 over length. This is 1 over length to the power 3 multiplied by charge. That's the units of density. And if you think about it a bit, that is it. So if you do that, then you get that the P, for example, is z. Again, z is in this direction. This is the direction of z, q times d, which is of course, exactly the same that we got before. There's nothing new here. It's just q times d, and it has a direction. It goes from the minus to the plus. This is the direction of this dipole, and this is exactly the expression that we had before. I'm not going to do this exercise, but if you put here this p multiplied by r, you'll get what we got at the beginning. Because z multiplied by r, what is z? Vector multiplied by r?
Cosine theta.
The cosine theta, not the theta prime, the cosine theta that we had at the beginning of the class. I think you still remember it, because you are young people, you don't forget. So this is the dipole moment. It makes a lot of sense, and it gives you the correct results. Griffiths discussed a subtle point, or not so subtle. I don't think it's too subtle, and that is about how to choose the reference frame. So, for example, here I chose the reference frame here in the middle. It's very useful. But, okay, so reference frame. There is a better discussion in Griffiths, but let's, just for simplicity, change things a little bit and say, let us say I wanted to have a reference frame, which is, this is point z equals 0, and this is point z equal d, and here I have this thing. Will it change anything? The answer is nothing. It doesn't change anything. All the results will remain, for the dipole, remain the same. However, there is one case where there is a little bit of subtlety, which we will solve in a minute, don't worry. Everything is correct here. Let us say that we have let us say that we have something like this: two systems, two references, but now I have plus 2q. How do I want to write it? Okay, so let us do it like this. Let's say we have one reference frame. Here it's q. This is z equals 0. And here I have 2q. And the 2q I'm going to take as minus, whatever. And then I can look at another reference. So this is reference frame 1. This is reference 2. And here I'm just looking at what is the dipole moment. I'm not looking at anything else. So, and just what is the dipole moment, and then I have here minus 2q, q. This is a distance d. What is the dipole moment here? By plugging into this equation, I start, you see, when you are at 0, this doesn't contribute, this one doesn't contribute, because there's an integration, and here r prime is equal to 0. So this one is not important. So up here, the p is minus 2qd z. But here, what is it? Now this minus charge is not contributing because I put it on 0. So this is now 0. And here, so let's call it reference 1. This one is reference 2. Now this is going to be qd z. And p2 in one reference is not the same as p1. But
Minus. P2 is minus.
Minus, yes, correct, because it's minus here. Thanks. So, but it's not the same, that's my point. But is it a problem here, or why does this happen?
Because the first moment has not vanished.
Exactly. So the total charge in this example is not 0, because the total charge is, here, this is minus. The total charge is minus q. So if the system is neutral, then, as I said here, the reference frame is not important for the calculation of p. But if it is charged, then you have to be a little bit careful. But then it's also very simple. What do? You simply take one charge out as the monopole, and then you are left with a system which is, in this case, minus Q, and then you have minus Q and Q. So this will be a monopole, and this one will be a dipole. And when you calculate the dipole from this part, it will be independent of the reference frame. And the monopole will give you the monopole contribution, which is trivial, which is 1 over r. So just be careful when you have a system which is charged. This is what Griffith says. When you calculate the monopole, the best idea is very simple: to subtract the mean charge and just create a neutral, effective neutral system. Treat separately the monopole and then the dipole on the rest of the system. Okay, so now we have this dipole. Yes.
אם אני מחשב את המונופול והדיפול לא סתם עם העין, לפי הנוסחה שעשינו, זה יצא מאליו ההפרדה הזאת.
You mean where? I mean, for example, here? Yes, but that is correct, but I mentioned before that this equation, in my opinion, has some disadvantage because you want to calculate a p vector once and for all, if you have it, and then for different r, you just plug it in here into this result here. So this equation is very useful compared to this equation. I emphasized already that this equation is also correct to calculate things. It's the same, these are the same equations, but this one is useful in the following sense that you calculate this P, someone gives it to you, you measure it, and then you have the potential of the dipole, right? And that's the benefit of that. But when you have a benefit, there is some small prints. The small prints is what I said just now, that be careful if the total charge is. Yeah, that's all. Okay, so let us go for a short break. And after the break, we'll discuss what happens when you have a material with many, many dipoles inside, or at least we'll start the discussion on this. So now we explained a bit what is a dipole, what is the multiple expansion, and now we have to understand something very physical. Dipoles are everywhere. One of the reasons for this is very simple. If I take, let's say, this wood is not charged. That is a very good thing, because otherwise, if you are also charged, boom, you'll be stuck to this. So dipoles are really found in every, more or less, in many molecules which are not totally symmetric, for example. So it's important. I mean, it's not just the second term in an expansion which looks so bad, but it is really something very physical and important. So what we are going to discuss now is polarization. Polarization field is the following. In dielectric materials, so again, we discussed a lot conductors, so now we're going to discuss dielectric materials. So obviously the properties of dielectrics are very different than conductors. For example, they don't conduct electricity, right? So this is obviously very different. They are common in nature. And their properties, electrostatic properties, are determined by something called polarization. This is just to say polarization is damn important. So what I want to explain this, but to understand polarization, there are two ways to look at it. One of them is more or less microscopical, And the correct way to treat microscopically these things is actually with quantum mechanics in many cases. And the other way is macroscopically. To get some physical intuition, you need to think about it at the beginning, at least this is my point of view, from a microscopical point of view. What is polarization? What is a dipole? When you look at it from a macroscopical point of view, you use Maxwell equations. So Maxwell didn't know, wasn't sure that atoms exist, but still you can treat this thing. And this is the magic of the 19th century physics, that even though they did not understand fully the microscopics, they could understand a lot from macroscopical observables without going into the fine structure. So, but I'll discuss this in a very strange way, in a very hand-waving way, from what I call classical microscopics, which is not correct, but it gives you the correct answers, more or less, order of magnitudes, but not exact numbers. So first of all, I want to discuss what I call induced dipole. Induced. Not Indus River, induced. Mushre. You know English? Is it clear, this word induced? Yes. Everyone knows induced is clear or not? Because I can teach you English. Okay, induced dipole. What do I mean by that? What is a kind of more or less physical picture is the following. Let's take the hydrogen atom, assuming you know something, and assuming that you are at low temperature, so you are in the ground state of the hydrogen atom. The hydrogen atom is an electron, has some density, that's psi squared more or less, but it is smeared there around the proton. The proton is the dot inside there. What is the dipole of this system? Nothing. There's no dipole. This is as long as the external field, external, is equal to 0. What is induced dipole? When I add from the outside an electric field, something will happen. If we think about it, what will happen? Let's say I add it like this. This is my constant electric field independent of time and space. It will distort the wave function. It will pull or distract the atom. And I claim more or less what will happen is the following. Assuming the positive charge is still a point, you will create an ellipse and you'll displace. This is a displacement, not of the Gaussians, displacement. You displace relative displacement of the proton. A little bit, but it's very small. Anyone wants to guess how big it is? Well, that depends on how strong the field. The stronger the field is, the more force you put in, the bigger the displacement, right? That's obvious. But we will calculate now orders of magnitude of this. So, here, external is not equal to 0, and dipole is finite. That's all what I want to say. So this is how I create a dipole with an external field, even though it didn't exist before because of symmetry. That's one option. There are other options. Now, to define it, what you then see, this is the dipole moment. Before I said this dipole moment, how is it given? By some charge density, which I didn't tell you where it comes from. But now what we see, that this dipole moment, in many materials, but not everyone, is proportional to E. These are actually a linear response. If the field is not strong, so, and if the system is symmetric at the beginning, then this alpha is, the bigger is the field, the bigger is this thing. And this alpha, what is this alpha? This is something that you can measure in principle. What do? You do an experiment. You apply a weak field. What is a weak in this case compared to the Coulomb field inside the hydrogen atom? And then you somehow, I'm not saying how, you measure the dipole, and then you change the E, and then you get this slope. you get this number alpha. So this alpha is, of course, depending if I do it for lithium, I do it for beryllium, different atoms will have different numbers here. And this will be very specific to the system. How do we treat this in quantum mechanics? I think you learned quantum mechanics too.
No.
Perturbation theory.
Perturbation theory, and what is the name of this effect? Stark. But not Stark for the energy levels, but Stark for the density. To calculate the density in perturbation theory. The zero order in perturbation theory is the famous ground state of the hydrogen atom, which is just exponential decay of the charge. And then you look at the distortion because of the external field, first order corrections to the ground state, then you have a density, then you can in principle calculate this thing. Yes?
in analog to...
It's not a course in quantum mechanics now.
No, I know. In analog to conductivity, the alpha was a matrix. Here it's the same or
right. This is valid for this, for weak fields. And then, okay, let us say, just look at dipoles. Of a more complicated object, which comes from the world of chemistry, and physicists don't like chemistry, but of course these exist. So we can have a dipole, let's say, of some object like this. This is a cartoon of a water. The water has a natural dipole, but let's say it doesn't. So I have here 3 balls. Then if I apply here a field in this direction or in this direction, it's not necessarily the same. And then this alpha P can be, alpha is a matrix times E. You can change the direction of the field, but here the simplest thing is to think about it as a number if the underlying system is totally symmetric with respect to all directions in space. So alpha can be also a matrix in principle, but this is way too complicated for us. Okay, so for example, let's say the electric field E is roughly 10 to the 4 volt per meter. Why did I choose this? If you know Stark effect, then in Stark effect there was 10 to the 6 volt per meters. This is a small, maybe you don't want to be electrified by this type of thing, but inside the atom it is a small number compared to the electric field, the electron field inside, so this is small. But not too small, of course. If it's very small, you cannot measure this. So then you can have a displacement. What is a displacement? Again, the displacement, let's say, roughly speaking, is very rough. The displacement of the positive charge displacement, and soon we'll define it. Anyone wants to guess how much it moves in this hydrogen atom, roughly? No, not alpha. The physical, this is in meters. So this size is 1 angstrom. Now I have this field. How roughly does it move? Okay, it's hard to guess. I couldn't guess. 10 to the minus 18 meters. My point is that this distortion is so small. It's like nothing in this field. But still, so 10 to the minus 18 compared to what? 2 angstrom. 10 to the minus 10, so it's 8 orders of magnitude smaller. So even though it's a very small effect, it's a measurable effect, and the reason is simply that in a gas, for example, you have many of these dipoles. You cannot measure one, you measure a Avogadro number, and they add up. But it's a tiny effect, but it is still important effect. The smallest distortion that you can imagine. I mean, I would throw this immediately to the trash, but still, you can measure this. So let us see what is alpha for the hydrogen atom, very roughly speaking. So what is the units of alpha? The units of alpha is the units of a dipole. divided by the units of an electric field. And this is 4 pi epsilon 0. This comes from the downstairs here. Here I have, okay, it's easy to show this is d to the power 3. Why d to the power 3? These are units. This is just very basic back of the envelope calculation. D is simply the E comes from 1 over, or if you want here, meter to the power 3. The E comes from, the E is proportional to Q, P is proportional to Q, and this is 1 over R squared in the units, so you get 4 pi epsilon meter squared. So what is the alpha? If you need to guess, what is the alpha for this alpha hydrogen atom? Yeah, so roughly, if I want to guess, this is not real physics, but this is the true physics for hydrogen only, of course, quote unquote. This is 4 pi epsilon 0 times radius Bohr. Okay, multiplied by some constant that you need to do some calculation, but the constant, the point of this constant is of order 1. I mean, this happens to be actually correct. Let us see this. So in these units, if I have alpha divided by 4 pi epsilon, a Bohr. So if I have alpha divided by 4 pi epsilon 0, what is this? What is alpha divided by 4 pi epsilon 0? For hydrogen, more or less. Okay, there is some constant that I cannot guess. 10 to the minus 30 meter. This is the number. Because Bohr radius is, but of course when Maxwell did all this theory, he didn't know anything about the Bohr radius, right? But he could measure these type of things. And how do we calculate things? More or less. So again, hand waving. So let us look at this model from a very simplified approach. So we use, it's not a model even. We have a charge density, and for simplicity, I'm not going to change the charge density of the electron because this will give you this constant. I'm just going to displace the positive charge. It's going to move because of the external field. What is this point? How is it determined? What is this displacement? There is an external field. And what balances this external field? It stops. The claim is very simple. It stops when the external field equal to the internal field, roughly speaking. What is the internal field? The internal field I can calculate if I create here a Gauss sphere. Inside, this is the charge density of the electron. This is the radius Bohr. This charge here has to balance the external field. This is how we will get in the magnitude of this shift, right? So if we do it, so the E external, let's do just units, is 4 pi epsilon 0 times density. What is this density? This is the density of the electron cloud. So now estimate it very, very roughly. So this is the density electron cloud. What? Yeah, but we will simplify it even more. Yeah, in principle, yes, but then I need to do an integral. I don't like to do integrals. I'm going to take it as a constant. And you can estimate it very easily and get these numbers here, except for the C. So yeah, think about what it is exactly, or what crime am I going to commit next, because everything I'm doing here is a crime. So this D is again this displacement. So I have this original point and now I'm displaced D, how much I moved. Okay? So this is the charge inside this small thing. If D would be 0, no displacement, the charge would be 0. So this is the charge. This is D squared. This is from Coulomb's law. And now I need to say what is this rho. So this rho is 1 over 4 pi epsilon 0. So what is rho? What are you going to, the simplest thing you can imagine is the charge divided by this volume. And let us assume this volume, it's uniform charge, just to simplify things even more. So it's 4 pi A0 A bar to the power 3 over 2 over 3 multiplied by 4 pi d to the 3 over 3. But all these numbers that appear here are total nonsense because I'm anyway not calculating anything correctly. So here I have the radius Bohr. I hope you see it from this density. What is this equal? Okay, this is equal to the external field. And this is the charge from the inside. This is a balance of electric field, which is the same as balance and force, because this positive charge, you just multiply the Q on both sides. So the point is the following. And what is this? D. So you see, here I have d to the power 3, and from Coulomb I have d to the power 2. So then I'm more or less done. This estimation of d. So d, quote unquote, equal, quote unquote, 4 pi epsilon 0 E external. Okay, E external. This is what we said before, right? We said that the dipole. Sorry. You need to divide by Q. You have this A cube. Thing is, I can't turn the sound off because of this protection. Okay, so if I go through all this calculation, you see here this epsilon the power 3, and then in this calculation, what do I get? I get D is equal 3, the volume. The volume is the volume of the atom. Epsilon 0 divided by Q times E external. But what do I want to calculate? I want to calculate the dipole, right? The dipole I need to multiply by Q. So multiply this by Q, then I get P, which is QD. And then if I add things up, I get this is equal 3, the volume of the atom, which is again proportional to A Bohr radius to the power 3. That gives you the 10 to the minus 30 times the external field. Yeah. Okay, so this is the summary. This very rough estimation, and this is alpha is 3V epsilon 0. So remember what I said before. I said alpha divided by 4 pi epsilon, 4 pi is 10, it's the same thing, is roughly the size is the volume. The volume is a squared. This is exactly what I said here, up to some constant. I hope you all see this. This is a very rough estimation of what is this order of magnitude of this very small alpha in this induced effect. So now we can go to a laboratory, not me personally, but some people did this. Or Griffiths simply quotes the numbers for alpha in different systems. That is really gas systems at low pressures. So there's no interaction between the different dipoles in the system. So 4 pi epsilon 0. This is like before I said this is roughly 10 to the minus 30 units. And the units now are 10 to the minus 30 meter to the power 3. I think now you understand where this comes from. And then we have different gases. So hydrogen, helium, lithium, beryllium, carbon. This is 6. This is 4. I'm skipping a few. Argon, 10. K. K is potassium. And here there are numbers, and I mentioned before this is this constant C.
Argon is not 10, it's neon.
Argon is not 10. Oh, sorry. So what is argon?
Argon is, I think, 18.
Right. Yeah, okay, sure. Because I can't see anymore, so 18 is 0. Okay, thanks. This one is 1, this is 2, and this is 3. Why did I have argon? Thank you. What is special about argon? It's noble. So let us see let us see these numbers. This is this constant 0.66, 0.2, 24.3, 5.6, 1.8, 1.6, 43.4. So what do you see here is something that when you think about it you can expect it. What is special about, let's say, this one and this one?
They are noble.
They are noble, and they are relatively, when you apply this field, they are relatively less distorted. This is the conclusion, because they are kind of robust. On the other hand, let's say these two guys, they are, correct me if I'm wrong, the first row of the, you learn chemistry or you just?
Yeah, doing chemistry.
Yeah. You see, chemists know real physics. So these two guys, this is a noble, and relatively to this area at least, okay, there are exceptions, it's very complicated because it's chemistry, but this is a noble, it's very low. These atoms don't like to be distorted, they don't create a good dipole, so to say, or the dipole is small, and while here and here, these come, this is the first line, first column in Mendeleev table. And these are systems where you have one free charge in the outer shell. So in the picture of shells, which are, you have the atom, which is very simplified, modeled as a hydrogen atom neglecting the interactions. You fill in shells. And then these ones have one electron free, and they like to, what do they like to do? To perform chemical reactions and give one electron. And this electron that is sitting on the outer shell, you apply electric field, then it moves easily, so to say, and this is why their alpha is big compared to the other guys. In principle, maybe you can calculate this with perturbation theory. I'm not sure perturbation theory is a good theory, but most likely this would be a starting point. The other guys, it's very complicated because they are atoms. They have many electrons inside. It's not trivial to calculate them, but if you do, then this is a totally different course, a microscopical course. Again, the main message is that this alpha depends on the material, so different systems behave very differently when you apply an external constant field. Okay, so this is the induced dipole of atoms. But as mentioned earlier, there are also natural dipoles, especially of molecules, that are just there. You let the system relax to the ground state, and a famous one is water. The water has a natural permanent. So we have induced dipoles and we have permanent dipoles. Permanent dipoles. But permanent is divided into two categories. So a permanent dipole on molecules, on some molecules, H2O. This by symmetry breaking has some dipole. But now the question I want to and this, by the way, okay. So now the question is, okay, we have permanent dipoles, we have induced dipoles, but now we jump to the macroscopical world because this is the subject of our course, and we can imagine the following: what will happen, let's say, for a gas of molecules? Will a gas of molecules have a macroscopical dipole? So what will happen? So what will happen? So microscopically, this molecule has a dipole. But does it have, when you have many water molecules together, does it have a dipole? The answer is generally, under normal conditions, with no external field, the answer is no. So let us imagine several microscopical systems. So one of them has permanent dipole microscopically. But these dipoles are oriented in very complicated ways, in all different ways. This can be in a gas.
Even in zero temperature?
Sometimes, but not always. But usually, yes. I'll soon refer to this. So this is like a gas picture. This is a solid picture, maybe solid state picture. So in solid state picture, you have regions possibly with all the dipoles are like that, and then all other dipoles are like that, and the other dipoles are like that. Okay? And then this is where you have zero electric field, and then you have other systems like the atoms. So here, no dipole, because all these are when you have E equals 0. So here, microscopically, there is a dipole. Here, maybe there is some dipole because of interactions locally. But when you average all these systems, there's no dipole because you have random vectors and they are oriented in different ways. But now when you add a field, add E, all these systems, but for very different reasons, will have a macroscopical dipole moment, because in this case, all of these guys will, let's say, prefer to look up. All these small regions will also want to look up. Maybe not all of them, but some of them. And in this case, what happens is you create these cigars, you induce a dipole. So when I say induced dipole, microscopically it can mean a distortion of the wave function of a nitrogen atom, but it can also mean, when you look at many of them together, just orientation of many of them together. The effects are very similar, and from point of view of Maxwell, all these systems, he could not distinguish them, even though the origin is very different. So sometimes when you look at a macroscopical system, you don't really know what's happening microscopically, but the effects are same. from point of view, you apply an external field and then suddenly all the dipoles are either created or oriented in one direction to create another effect called polarization. Okay, so this distinction is important, the origin of which the microscopics can be very, very different. So just one last thing that I think you know before we go into the details. What is the torque? This is a reminder. I think it's a reminder. What is the torque on a dipole? It is rather easily, this is torque, sometimes this is tau, but we have tau for something else. This is P dot E. This is very simple to understand, and I think you saw it. Let's say you have two charges, minus Q, plus Q, and then you have here an E, and then you have F minus, and here I have F plus. Then if I calculate the torque, because this gives you this distance d, you get this, I think, well-known equation. If you have this torque, remember, what does the torque do? It's like a force, but what does it change? The angular momentum of this object. So this is this dipole here. So this n will, if it exists, will create a change, like Newton's law, on the angular momentum of this dipole. So it will start rotating if this is constant. And then another well-known equation that you can derive by looking at work is the potential of a dipole. It's P dot E, which means that this is equal minus P absolute value E external field E multiplied by cosine theta. And the minus here is important because this means minus the cosine, this U looks over PE as a function of theta. Theta is the angle between P and E, and it looks, it's minus, so cosine 0 is 1, and here it's minus 1, so it's something like that. This is theta equals 0. And the point I want to make here, and this is well known, is that this point down here, this potential, which is a function of theta, this is a stable point, while this is an unstable point up here. So it means that the dipoles want to align in the direction of the field. So this I used here when I said I add the field and then the dipoles point up. This is a good picture at 0 temperature, where all the dipoles want to go to the lowest energy possible, which is this one. So the lowest energy possible is P parallel to E, lowest energy. And it's easy to show that this is a stable point. If you don't remember this, then what you do is simply you look at, let's say, the torque, and you use a small angle. So this is PE sine theta. So this is P E theta when sine theta is proportional to theta. And then what you do, or this is what I do at least, what you do with this, you look where is the change of the angular momentum. So if I rotate, so this situation plus minus is a stable situation, then I rotate the dipole a little bit with an angle theta, I create a torque. The torque wants to create, gives you momentum. What is the momentum? Angular momentum. And it will want to put you back. That's the point. If you switch it, that is the kind of a little bit delicate part. If you switch it, it's the opposite, because this is this point pi, it's an unstable point. So you have one stable point and one unstable point, and parallel is the stable one. This is the minimum of the potential, which is given here. And this can be explained by using the torque. Okay, so these are basic equations about these objects, and we are using this one especially when we say that P wants to align in the E direction, that it comes from here, from this well-known equation. So now with this introduction, we have some general thoughts. What is this microscopic P, or you apply a field and then some polarization induced, but let us define polarization precisely. So in typical situations, but not all situations, when an electric field is applied. By the way, this was a remark. So some systems, this is back to your question, can be polarized without external field. But when you were in kindergarten, you got a magnet. You didn't get such an object. So they exist, and they are called ferroelectrics. But it's a super rare phenomena. It's not typical phenomena. Unlike the magnetic fields, that there are many naturally magnetized fields. So it's interesting why we do have a lot of magnets in a natural way and not so many corresponding electric magnets. But they exist. But it's exotic. That's an answer to your question. So this is not the whole story. There are systems where zero fields still have polarization. I have to emphasize this. So when an electric field, this is a typical situation, is applied on a dielectric, we get something called polarization. It's a field. It's a function of space, and it is denoted by P, in principle X, Y, Z. And what is this P? It's very simple by definition. It's the dipole moment per unit volume. What is it meaning exactly? I have some material and some charge distribution, whatever it is, and I take a small box here, and inside I have many P's, P1, P2, etc. I add these small P's together. This gives you the dipole moment of this small element, exactly like I did when I summed up charges, but now I'm summing up vectors. And the sum of the vectors, the sum of the microscopical dipoles give me the local polarization. Of course, let's say all of them are in one direction. The bigger is the box, the more you have. So it's the density of these dipoles per unit volume, And this is the field. So one way to think about it, if I measure here the dipole here somewhere on this spot, and I average over all the microscopical dipoles, I'll get this dipole, effective dipole, which is this capital P, but again, it's per unit volume. So P times delta tau will give you the dipole itself. Okay. So now, hopefully this concept, but again, this is confusing at this stage. This P is related to the E usually, but not always. The exception of ferroelectrics. So now we are going to get to the main point of this part of the lesson of this, and that is a beautiful theorem which tells you what are the electric fields in principle by means of integration, given that you know the polarization. Now I'm changing a bit the mindset. Before I said I need an electric field to find the polarization, right? But now forget about that. Let us assume that we know the polarization. We either measured it, or it's a ferroelectric, or something. Let us assume I give it to you. And now I want to calculate the electric field. So I have a material like this, and it has these different dipoles, and here's some type of dipoles, here are the dipoles. They sum up, I have this polarization field. Now what is the electric field, let's say at this point? Okay, the question is clear? So, the answer. So, this is the question, what is at some point R in space? What do we know to solve? What did I teach you up till now? We always like to go back to problems that we already know. So wouldn't it be nice if we had, instead of this damn polarization field, which is complicated, right? It's a vector. I want to replace the system with a charge density and the charges on the surface. If I manage to do that, I'm going back to usual electrostatics. That is, there is some charge both inside and on the surface. Use the usual tools to calculate what is the field here. And this is what we are going to do now. We're going to show how to go from this polarization field, which is the sum of these local dipoles, back to the thing that we are expert at, which are charges and on the surface and in the bulk. So I'll start just by the statement, which I think is very nice. So the potential created by the polarization field. What I mean by potential? The potential from which I will calculate the electric field. So maybe the best way is to think that these are fixed. There's no external fields here. Just these are fixed somewhere. I put the dipoles with a hammer and put them just here. The potential field from which what do I derive from the potential? The usual electric field. The potential and hence the electric field of a system with given, I need to know what is this polarization field. So I have some medium, and here I have some P here, and it changes inside. Is the same as the potential created from two things. A, charge density, bulk charge density, rho B, equal div polarization. Remember, polarization is dipole, it's Q times E. If I take the D, the div will give you Q, but it's per unit volume, so this gives you the correct units. At least the units are okay. B, and in addition to this bulk charge density, surface density. Surface density is given units of charge divided by surface, which is meter squared, which is sigma B P dot n. What is n? So I have my volume, and I have n is a normal to the volume, and I need to know P here. Remember, this is a continuum description. And then I have this charge P dot n. So I replace this complicated vector field with another problem where inside I have PB and here I have sigma B. Sigma B and PB can depend on coordinate, can be very complicated by themselves, but okay, then I'm done. So if this is true, then we are going back to the previous problems. In principle, at least, you know how to do this, right? So I think this is very nice. You read about this in Griffith? Yeah. You didn't read about this in Griffith? But you should read about it. It's a really beautiful theorem. And this is what I want to prove now. But before proving it, I want to build some intuition. Because what am I saying? Why is... Maybe let's start with the easier one, which is this one. Why does the density, the polarization field on the surface model sigma B? So I should have asked ChatGPT, but I asked myself, and I'm not so imaginative like Chat. This is what I came in my explanation for this. So let us look first at a system where the div P inside the system is 0. That's just for simplicity, right? And I'm going to build a very specific system, but maybe this can teach you something. So I have a box, because physicists love boxes. And I'm going to put here dipoles. But I'm going to, it's very specialized. I'm going to put here dipoles in layers. Oh, no. So this is layer number 1. This is the, I just put here dipoles. This is layer 1. Layer of dipoles. What do I do in the second layer? I put more dipoles. And I'm going to do it like this, which is not the most general case, of course. And then plus, and I'm just going to have 3 layers, but because I'm lazy. So we have here, there is no, of course, this picture is not exactly correct in this language, because in this language we have a continuum description, and here I have discrete description, so it's not precisely the same thing. But intuitively, I think this picture helps, because if this, in this case, let's say that these guys are very close, I'm going to just wipe them out. And you see what we are left with are these charges up here, and these charges down there. And this is exactly the same as this formula here. See, here is the P dot n. There is a P in this direction. Here there's a P in that direction. Here you have negative charges. Here you have positive, or the opposite way around. So I hope this is useful for you to just to start thinking about it. It's not a proof of the theorem, but this is one way. Now let us build another system. Why is div P so important? We're going to do a similar trick, but more complicated, because here there's no div P. Here div P is 0. So let us write the same system plus, 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 plus. And this is the first layer, so I'm not playing with the microscopical dipoles. But now I want to create a change in the density of dipoles, because I want to have div P not equal 0, right? So what do I need to do in this layer? I'll put simply less dipoles, just for plotting. So let us plot here plus, minus, plus, minus. Right? How many layers do I need? That's important. So yeah, again, every plus has a minus, Every plus has a minus. This is layer 2, this is layer 1, but the number of dipoles is changing. Here they are high density, and here there's low, so there is a divergence is not 0 here. And then I want to add, the last layer, let's put it like the first one, plus, 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 minus, 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 and this is in this box. Now we do the same trick as before. Let us look what are cancelled. These guys are cancelled. These guys are cancelled. These guys are cancelled. These guys are cancelled. This one is the charge density on the surface like before. But here we have more charges in the middle. So this effectively, the system is like this. Plus, 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 plus. Here we have minus, minus. Minus. Okay, sorry, plus, minus, minus. And here I have plus, 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 minus, 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 minus. Now, here the first layer compared to the second, so the density is high. Here the density is low. Low in what? Here I simply have only 2 dipoles, so the density is low. Here the density is high again. Again, the density of the dipoles. So when I go from up to down, you see the density, or the polarization if you want, which is related to this P, it changes first in one sign, and then the other sign. It goes up, down, up, like here. Up, down, up. And indeed, what you have in the effective system is here minus and here plus, because the div P is changing sign, if you see along this direction. So this is a kind of hand-waving intuition, but now we are going to prove this and see how it works. And then later we can use it to solve all kinds of problems with dipoles. So let us prove this wonderful theorem. It's wonderful for a teacher because then you don't need to teach anything, because you say, it's the same as the previous problem. Then, assuming the students know the previous problem, then we are done. But no, it's also very physical and very beautiful. So the idea is, let us start with the dipole that we had already. And here I'm going to introduce P, microscopical P. So this P is the dipole inside the medium somewhere here. This is why I add, it's a small P. It's a real dipole. And as before, this is dot R, 4 pi epsilon 0, R to the power 2. So what am I going to do? I'm going to take a real material. The real material, there is some distances between the charges. I'm going to squish it, and I'm going to think about the material microscopically as dipoles. So this is the potential of this field. And now I want to use the superposition. So I need to add many of these small p's, and many of them, their contributions inside the, which means doing an integral. And then I'll get the macroscopical potential, not coming from one of the dipoles, but coming from many of them. What do I like here, and what do I not like here? The whole trick is, here I have 1 over r to the power 2. I'm going to try to make this into 1 over r with some tricks. If I have this 1 over r, then what? It's like the Coulomb problem. That's the general strategy. Let's see how this works. Before doing that, and before using this, so this is just the background, let us remind you of some simple mathematical statements. 1 over r prime. The grad of this thing, what is this thing? You know this from high school. What is this thing?
1 over r squared.
Yeah, because it's either.
1 over the distance squared.
Yeah, why? Because this is like the potential of a charge, and then if the potential is 1 over r, then the field is 1 over r, and then this is what it's saying. It's not a delta function. This is equal to the following, and these are notations which we are already used to, I hope. With the hat, which this is the unit vector of this thing, r minus r prime squared. So again, going from potential, going to electric field, this is standard. But if you don't believe me, then take the grad and operate on r, for example, and you'll get this thing. Okay? This is easy to prove. It's 3 lines, but it's already late, so we'll skip it. Second equation I'm going to use, it's also a very, maybe you are not familiar with this, but you saw it a million times together. Or what do I mean? You saw something very similar, so you, with some imagination, you can understand it. So div of f is some function of x, y, and z, and it's a scalar. And a is a vector, some vector a. Okay? So what does this remind you?
Exertion.
Yeah, the derivative of multiplication of 2 functions. But here there's a vector. Okay, so you separate the vector. You have ax, a y, and z. You do it for each one of them, and then here you have derivative x, y, z, but it's trivial. So I'll just write down the result. This is f div a plus a grad f. And like the derivative of multiplying 2 functions, you get 2 terms. One where the derivatives are acting on a, and one where the derivatives are acting on f. But the only thing you need to remember is that, you know, this altogether is going to be a scalar, and then you need to remember what is the div, what is the grad. But okay, this is a simple thing to understand, or we will assume it is simple. And these are going to be the 3 tools. One is the physics, microscopical dipole, and this basic electrostatics, and this thing. This switching of 1 div into 2 will give you 2 contributions that I mentioned before, rho b and sigma b. So this is how I'm going to create two effects. So what is, now I want to relate between this microscopical p and the macroscopical one, d tau. So by definition, the local dipole moment is like the polarization times delta tau. This was just a definition. You need to take the volume. I mentioned per unit volume, it was here, and then you just multiply, and then you get this this definition. And then what is V of r? I'm using this equation, so I need to do the following. I need to integrate 4 pi epsilon 0. This is this one. Okay, so let us write down the system coordinate. So here I have r prime. This is the state, and here is r. This already you had. This is where the observer is. This is where I integrate, and I integrate over the whole volume. This was similar to what we had previously, but what is the new difference? I'm using this one. So what is this distance here? It's r minus r prime, right? The usual thing. So this distance. So this one has to go inside here, and I need to integrate over r prime to get the final result. So this is equal capital P of r prime r minus r prime r minus r prime squared d tau. Hopefully you understand this integral, because we had similar integrals before. So what does it say in word? We have many dipoles, we sum them up together. We look at the distances by varying, integrating over d tau, changing this r prime. I have many different distances here when I integrate over all of them and I sum them up. And this is simply using this dipole equation. This is why we have here 2. The important number here is 2 instead of 1 that we had before, right? When we did the same thing for charge density for the Coulomb law. It was very similar.
It's not supposed to be E of R, the electric field.
No, because this is a dipole. Remember the dipole, the potential goes like r squared. That's the whole point. But you are right. If you were in a, yeah, this is the point. We don't like this 2. We want to go back to 1. If it would be 1, it would be like a charge problem. So now I look at my tools and I say, aha, what is this thing? It's this grad. I'm going to replace it with a grad. And then, okay, let's see what happens. So I'm using the grad. So, what is the potential? Maybe up here. V of r. Okay, it's the following thing: 4 pi epsilon 0. Maybe we call it. So here I used. This is this one, and this is, later we're going to use it using, so, no, without the, so this is 4 pi epsilon 0, integrate, this is integral over the volume of the, where this polarization field exists, okay, volume, P of macroscopical polarization field times grad, but I do it with respect to the r prime. Here I have a choice. I can do the grad with respect to r or r prime. What will be the difference? Will be a difference in the sign, because otherwise r minus r prime or r prime minus r. So this small chupchik is just, I'm using the integration variable. Why am I using the grad with respect to r prime? Should be clear to you. Because I'm integrating over this delta tau. This delta tau depends on r prime. So then I'll have here the derivative with respect to what I integrate and not with respect to the field that I'm having, that is just a constant. This r position is r. So this is a grad with respect to r prime. And this is 1 over r prime and d tau. Now I'm happy a little bit because this is Coulomb for me. I could read. Now it's to the power 1. But there is this damn grad here. So what do I need to do? Now I need to use I need to use this thing. So this thing gives you a grad. This is a scalar. So this corresponds to A. What is A? A is this P, polarization field. Yeah, I have this grad, and then this will be replaced by 2 terms. One of them corresponds to this term when I'm going to go on the other side, and this term. Okay, that's very simple now. So this is equal V of R 1 over 4 pi epsilon integral over the volume. Now I have two terms. P of R, the polarization field, which is given by God here, and times. Okay, so the first term is this one actually. So here I have div, sorry for that. PR divided by R prime, a bit messy, minus d tau here I have R prime div PR prime. So just let us look only on this term. Here I have, this was my A. Now I have div A, that is this div P. And F, what is F? F is this function, but with 1. But what is this integral? Let's focus on this integral. This is the Coulomb law, and this, if with the minus sign, I get this charge density. So let us define, as I did before, rho bounded, B is for bounded, also for bulk, but bounded charge it's called, is minus div P. And then you can immediately see this is like usual electrostatics. And the minus is important. This comes from this minus with charge rho B. But this is a volume integral, and also this one is a volume integral. And what did I say before? The surface is important. Now we need to go to the surface.
We can use like the Gauss theorem.
Gauss. You're a mathematician, you call it Gauss, and we call it the divergence theorem. Right, absolutely. So here I have div of something. Now, the way I remember, one way to remember this thing, if you have a derivative of a function and you integrate it, it must be simple. But it's not exactly simple because it's a div and it's a three-dimensional integral, and that's why we needed Gauss and not Leibniz. But Gauss solved this in something called the divergence theorem, where you replace an integral of a volume of the divergence with an integral over the surface. Right? So with the divergence theorem, we are nearly done. So this is now divergence theorem. You know, I found out, you know, that Gaussian distribution is very well used in central limit theorem and diffusion and many things. But who invented it?
De Moivre.
Okay, de Moivre, yeah, well, in a special case, you're right, but actually Laplace derived the central limit theorem. So it wasn't Gauss at all. So I hope that also in this case it was Gauss. But okay, history is very weird. Okay, so we can use the divergence theorem and go to an integral over space, over the surface, and then I'm just using it. V of R is 1 over 4 pi epsilon. P of R prime dot n R minus R prime. The good news, it's R minus R prime. This is again back to Coulomb from physicist's point of view. Right? So this is a charge on the surface, but this is a charge on S, on the surface only. This is for surface. So I have this thing and I just integrate over here. And I got rid of the div, and now I have just an integral over the surface. And I'm going to call it ds.
ה-P הזה זה עדיין ה-P של הנקודתי כאילו? או שזה כבר הפך להיות ה-P
this one and this one are related, but they are not the same units. Because, again, the big P is polarization per unit volume. Yeah? This is the volume. This is a meter to the power 3. This one is just the dipole itself. But they are related in this approximation. What we actually did here, we have dipoles that have some distance. We quashed them and made them point dipoles. This is the meaning of the uses of this one. Okay, so now if you know this PR, then this polarization field, this is what we called, what did we call this? This is what we called sigma B, and this is to the power 1. This is Coulomb. So we are back to electrostatics. Here we have minus, just copy this, R minus R prime, again, familiar Coulomb law. And that is it. So to summarize, we need the charge density. This is what I called before rho, including the minus sign, rho B. We have the charge density, we call this junk. Surface density, charge density in the bulk. This is a volume integral, this is a surface integral. This is like an electric field coming from a surface charge. This is like a potential field coming from a bulk, inside the bulk, and yeah, we are done, right? So this is a very nice thing. We finish the proof, and then we can go home soon, and we can solve problems in the same way we solve problems in electrostatics, if you know the P. Later it's going to be much more complicated, because remember, this capital P will depend on some external field, but for now I left this out. I simplify things, I assume this is, we know this, and I calculate things. Okay, so it's not the end of the story, because how this is created is a different story. So there are many stories here, it's not one story. Before we go, we're going to do a very quick, oops. We're going to do a very quick exercise, just so it will, maybe now it's so late you don't remember anything already, but maybe I'm wrong, and maybe later you can read it in Griffiths or go over this and do things. And so let us give a very simple example that will hopefully further clarify things. So the question is like this, a simple question: what is the potential stemming from a sphere with radius capital R, with a polarization P, which is constant. What I mean is it's independent of space. So you have a ball, radius R, and here I have P, capital P. This is the problem. That's it. So what is going on here? So what is div P? It's 0, simply because P is a constant independent of space, so div P is 0. What does it mean? I need to take this problem. What are the charge inside? Nada, nothing. 0. But there is, of course, there is some charge on the surface. So from here I get rho B is equal to 0. What is the charge on the surface? It's P dot N.
Yeah, which is all.
What is P dot N? P is in the Z direction. What is P dot N?
Yeah.
In the usual coordinate, yes, it's simply cosine theta. So P dot N is simply P absolute value cosine theta. So what does it mean? This is sigma beta, sigma B. So we have a sphere now. This is the original problem with the polarization. Now we have a different problem. What is the charge up here? Some pluses. And here there's a lot of charge. Here there's much less charge because theta is, and what is down here? Minus. This is the effective problem that I'm solving now. I replace the polarization problem with a charge problem. Okay? And you understand this is theta equal 0, this is theta equal pi, here it's minus. What is the total charge?
0.
Of course. This is, when I say charge, total effective charge, right? It's not the real charge, I mean, it's also the real charge, right? But total charge, if you want, is 0. Because what is the real charge? What do we really have here? We have plus, minus, many dipoles, right? So, also they have the total charge is 0, but these are the effective charges I'm talking about. And then we need to find the electric field, the potential field, both inside and outside will do it. So what is it? Let us give first the answer for simplicity. And then solve it briefly. What is going to happen here? What is cosine theta? I asked you this question today, but it's so late, maybe you forgot. Yes. What does it mean about the quantum number L? Okay, soon it will appear when we solve this, but now I'm not solving, I'm just telling you what is the solution, and you can check it for yourself at the beginning. VR and theta I claim. So again, we have a sphere, and then I have R, and this one is theta, right, relative to the z-axis. There's no phi dependence, this is obvious, and this is the following. It's the absolute value of P, R cosine theta divided by 3 epsilon 0. Of course, the number 3 you cannot guess. This is for R less than R. This is inside. And what is it outside? It's actually possible to guess. So, what is happening inside? What is R cosine theta? This thing is simply Z. Right? R cosine theta is Z, usual thing. So what is the field inside? The electric field. If you have a potential going in Z, that just depends on Z.
It's constant?
It's constant, but its direction is Z. That's all, because I need to take, yeah, it's trivial, right? I mean, it's like the gravitational field depends on Z, and then the potential then. So what is this one?
Dipole.
Why is it R? Yeah, right. R to the power 2 reminds you of a dipole. So the whole object outside behaves like a dipole, and inside is a constant field. This is the solution. So
how can it be that the field is not 0 inside if there's no charge inside? I can take like a Gauss envelope.
No, but it's not symmetric.
but I mean, you can take whatever you want, but the field is constant. Then you have here a sphere, then flux in, flux out, totally 0, and then these are the charge fields, and then this one is looking something like that. What a wonderful cockroach. I think I plotted it correctly. What does this tell you? Why are they going out here? Well, the charge is positive on top, so it's going out. and it's going out like a dipole. This was the picture of the dipole that we had before. Here it's going in because of this negative charge. Here we have a plus, here you have a minus. So the field goes down, and this is this solution. Okay, how do you derive this solution? So, okay, inside, constant field, electric field. In the z direction, in the minus z direction, outside, like a gigantic dipole. Why do I say gigantic? Because we have here a macroscopical object, and it's composed of many microscopical dipoles that created the polarization field, but altogether it just gives you one big dipole. Of course, here is this constant p. If this p is 0, then everything is 0. This is obvious. So, as a reminder, or an exercise, how do we solve these type of problems? This is done easily, or more correctly, with the usual techniques that we studied already. We explode the phi symmetry. And of course, in these problems, and this is the difficult part actually, is to determine the boundary conditions to solve these problems. This is the, in my opinion, the most important, tricky part of these things. So I have for r less than r, based on our previous lessons, this polynomial Legendre, in principle AL, RL, PL, cosine theta. We showed this previously when we solved the Laplace equation. I just remind you, the general solution has also terms like 1 over r to the power L, but I'm working now inside and I do not want the potential to diverge in the r equals 0, so I throw away half of the terms. The opposite happens outside. This is sum L equals 0 to infinity. This is r bigger than r. This is outside. This is equal to sum dl. Here you have RL plus 1 PL cosine theta. Now, as you see from the solution, you don't have an infinite sum. Eventually, most of these ALs and the BLs are 0. And not only that we don't have infinite sum, we have this cosine and this cosine here. Where does this cosine come from? It's obvious. From the charge density, which was equal to cosine. And it comes from mathematically from P1, but it comes from the charge density was proportional to this cosine field. So what are the boundary conditions? Is that V R, I'm going to write it like this, VR plus. What is VR plus? It's a little bit outside of the system, outside of R. R plus epsilon, if you want, epsilon goes to 0. Is equal VR minus, and the thing to understand, or something I think you know, is, okay, let's write it without, minus dV dr in, this is minus P cosine theta divided by epsilon 0. So yeah, this is, what did I do here? This is something you know. I used the Gauss on the surface. So there is a jump in the electric field, as usual. And here I use the charge density. This is my sigma b, right? So I use the sigma b, which is given by the polarization, okay? That's the whole trick. So this is given by polarization. I mentioned this, given by polarization and by the theorem that I stated that you need P dot n And P dot n was, this is the absolute value, P dot n was cosine theta, and you can think about the sign. And then solving it, it's easy to show, and I'm not going to show. This comes from here, because when I plug it here, only the L equal 1 is important. So only L equal 1 important. Hint, because P1 cosine theta is equal to cosine theta, like CB. So like CB, this sigma B, this is sigma B. It depends on the cosine theta. So it's easy to show, relatively easy to show that all the other guys are vanishing. Just plug it into these equations and match, simply match term by term, and then you'll see that only the L equal 1 has this term, and then you can easily solve it, and the other times this term doesn't exist, and then you get 0 equals 0. As can be shown, but even if you don't believe me, you can say, let's guess L equal 1 and find that this is the solution. Then it's kind of pretty easy, because then I get from here, let's look at this. This is the out. I take the derivative when L is equal 1. Okay, so from this one, I get B over B1 over R to capital R. L is equal 1, so here I have 2. I can use the cosine, but I can also use, let's take theta equals 0. So this goes away. It's true everywhere, but okay, you can add the cosine if you really want. This is equal A1. This is here with L equal 1. This is also cosine times R. This is from this one, and then I have this one. The derivatives. So if you are out, you are here. Then this is BL R to the power 2. Then I need to take the derivative. It will be R to the power 3, and here I'll have a 2 and a minus sign, if I didn't make a mistake, multiplied by cosine. That's the polynomial. Minus, now the in, I have this one, so this is simply A1 cosine theta, and this is equal minus P cosine theta epsilon 0. So I can cancel the cosines, and I have, this is 1, sorry. And then I have two equations. I mean, I can express B1 as a function of A1, and then I can plug it in here and get A1, and then I can solve the problem. So you can find A1, B1 easily and solve the problem. And the solution is what I discussed at the beginning. Okay. So here we will finish. Please read all of chapter 4 of Griffiths. Hopefully beginning of next lesson we will complete it, and maybe if we are lucky we will also start chapter 5. So if one of you wants to read further, then please go ahead. Chapter 5 will be about magnetostatics, then we have magnetostatics in material, and then we go to dynamics and to relativity. Okay, so thank you very much.
Thank you.